Kia ora team, welcome to the 2021 Level 2 Chemistry Structure and Bonding exam worth a whopping 5 credits. Let's crack into it. Question 1. Rocket Lab is an aerospace company that launches satellites into orbit from Mahia Peninsula in New Zealand. So they use the electron rocket. Some substances used in the electron rocket are shown in the table below. So they've got oxygen, copper and graphite. We need to state what solid, type of particle and attractive forces there are between them. Classic question. Okay, so type of solid, oxygen. Because this is found on the right hand side of the periodic table, this is going to be non-metal, and when there are more than one non-metal atoms joined together, we know that it's going to be a molecule. So the type of particle is going to be molecules, that's what it's made up of, and the attractive forces between these molecules are going to be weak intermolecular forces. So between molecules is inter, and then the atoms which make it up are bonded together by covalent bonds. Do not get those mixed up. Molecules bonded by weak intermolecular forces, atoms bonded by covalent bonds. Copper. Well, this is on the left hand side of the periodic table, so it's going to be what? A metal. It's a metallic solid. The type of particles it's made up of are, what are they made up of? Atoms, or you could say cations, in a sea of delocalized electrons. So the bonds that occur within them, between these atoms, are metallic bonds between the cations and the negative delocalized electrons. Graphite, it's made out of carbon atoms, and this is just one that you'll have to remember. It is a 2D covalent network. So covalent networks, the ones that you should remember are graphite, which is 2D covalent network. Then there's diamond, which is 3D covalent network, and there's silicon as well. Okay, so these are the three main ones. And so let's look at the type of particle it's made up of. It's made out of atoms. And finally, the attractive forces between these particles are going to be, remember, the forces between atoms are going to be covalent bonds, which are very strong, by the way. Okay, copper is used for electrical wiring in the rocket due to its ability to conduct electricity. Let me highlight that. Conduct electricity and be stretched into wires. Use your knowledge of structure and bonding to explain both of these properties. So, based on what I've highlighted, what do we have to do? So, structure and bonding. Copper is a metallic solid made up of atoms in a 3D lattice held together by non-directional metallic bonds. These bonds occur between positive metal nuclei, which are fixed in place, and delocalized valence electrons. So a tip for you, whenever you talk about structure and bonding, use the table. So you talk about the type of solid, then you talk about what it's made up of, and then you talk about the attractive forces and bonding that occurs between what it's made up of. Okay? So in this instance, just for those of you who don't remember what the structure of a metal is, as I said before, there are going to be these positive nuclei in a 3D lattice structure. Okay, pretend this is 3D. And then you're also going to have valence electrons, which are basically flowing around, okay? They are called the sea of delocalized electrons. They're not fixed in any place, but the positive nuclei, they are fixed in place. Because these electrons are flowing around freely, the forces of attraction between the electrons and the positive nuclei are constantly changing. This is what makes it non-directional, because it's constantly changing. all right? Because the electrons aren't fixed. So, next we need to talk about property 1. Due to the non-directional bonding of metal bonds, the metal atoms can move past each other without disrupting the metallic bonding, okay? This is why copper can change shape and be stretched into wires, okay? So anything in pink is worth an achieved, okay? And then anything in blue, stating things in blue, is worth a merit, okay? So I've linked the fact that it's non-directional to the fact that you won't disrupt the metallic bonding because it's non-directional bonding, and I've linked it to the context. Green is for excellence, but you can only get excellence once you've talked about everything in the question, and I've only done one property now, so we haven't earned that excellence yet. So let's have a look at property 2. Copper is known to conduct electricity because of the free delocalized valence electrons. As a result of these free-flowing charges, it's important to mention free-flowing charges, this allows copper to also conduct electricity. So, by explaining everything, especially these, okay, we have gotten ourselves a lovely excellence. Next question. Okay, liquid oxygen is stored in the oxygen tank of the rocket. This tank is made up of a carbon composite material which contains graphite. Under atmospheric pressure, oxygen turns from a liquid into a gas at 183 degrees Celsius, while graphite must be heated around 3,600 degrees in order to turn from a solid into a gas. Using your knowledge of structure and bonding, explain the large difference between the temperatures at which each substance turns into a gas. So, structure and bonding. Remember, anything in pink is achieved with an achieved point, anything in blue is merit, and green is excellence. Oxygen is a molecular substance made up of molecules which are held together by weak intermolecular forces. Since these forces are weak, less energy is needed to overcome these intermolecular forces. Therefore, the boiling point of oxygen is low for it to turn from liquid to gas, and I've specified that temperature here. Okay, next is graphite. Graphite is a 2D covalent network made up of layers of carbon atoms arranged in hexagonal rings. Okay. Might need to look up an image of this if you cannot visualize it. These atoms are held together by strong covalent bonds, which take significant amounts of heat energy to break. This is why graphite needs a much higher temperature of around 3,600 degrees Celsius to turn from a solid to a gas or vaporize. Okay. So, to get merit, you need to either talk about the forces required to break the bonds for one thing. It could be for either oxygen or graphite. These are the achieved sections here. Okay, these are worth achieved points. And then finally, it's important to link back to the exam question. And so, the last part of the question is asking us why there's a large difference between the temperatures, and I'm answering that here just to wrap things up. Therefore, the large difference in temperature to change to gas or vaporize between oxygen and graphite is due to the strength of the attractive forces in each substance. So the stronger the attractive forces in a substance, the more heat energy is needed to overcome and break those bonds, okay? And you got yourself an excellence if you talked about these points here, all three, okay? All right, let's roll into question 2. So the electron rocket uses RP fuel, which is a high-grade kerosene, and it's a mixture of hydrocarbons, and this is the formula over here. Gaseous kerosene reacts with oxygen gas in a combustion chamber and the rocket is shown below. Which diagram below represents the reaction profile for this reaction? So it's either going to be diagram A or diagram B. What is it going to be? Well, the clue that we've been given is the delta RH value. As you can see, it's a negative delta RH. So what does this mean? The reaction is exothermic. What does exothermic mean? It's releasing energy to the surroundings. So if the reaction is starting off with some energy over here, and that energy is being released, the energy of the products is going to be lower than the reactants. So which diagram shows the energy of the products being lower than the reactants? Diagram A. So that's what we've got over here circled. That's why this is circled. Okay, and that's the process you'd go through. Okay. Explain your answer. The enthalpy of the reaction is negative, which suggests the reaction is exothermic. So that's worth an achieved point. This means that the reaction is releasing heat energy. That's worth another achieved point to the surroundings. As a result, the reactants start off with higher energy. As the heat energy is lost, the products end up with a lower energy than the reactants. Okay, so that's worth a merit, therefore resulting in a negative delta RH. This is reflected by diagram A, so all of that is worth a merit point. On the diagram that you chose above, clearly label the change in enthalpy. So I've done that already, and that's worth an achieved point. So how you do that is you take a line, dotted line from the reactants, and a dotted line from the products, and then that gap in between those two dotted lines is the delta RH, so that's showing the change in energy. So in this case, the change in energy is negative to show that this is an exothermic reaction. And the change in enthalpy up here is from the reactants to products, and it's going to be positive enthalpy. And that's how you draw the diagrams for a lovely achieved. Okay. Many rocket engines run fuel rich, which means that they do not use all of the kerosene. So in this case, the rocket is using this much of kerosene. In grams. We're always dealing with grams, okay? So only 75% of this is used, combusted, okay? We want to calculate the energy produced by the combustion of this amount of kerosene fuel. So the first thing that we have to do is we have to convert the grams used into moles, okay? That's the first step. That's always the thing to do whenever we get something in grams. First instinct, convert it to moles. How do we do that? We use this formula over here, okay? So, little m is the mass, big M is the molar mass, which is provided here for kerosene, okay? And we have to be mindful of the fact that 75% of this many grams is used. So for the mass, we have to show that 75% of this is used. How do we do that? Well, 75% is basically, we're converting it into a decimal. This is what we do in maths. 75 percent means out of 100. So that becomes, as a decimal, 0.75. 75% of is the key word, of this value here, okay, is going to be converted to 0.75 times. The equivalent of the word of is times, okay, fun maths fact, of 2.56 times 10 to the power of 6, okay, and that's how we figure out how much fuel is actually used. Okay, so I've written that here, a little bit incorrectly. I've used kgs instead of grams, so I'm quickly just going to correct that, my bad. So 6, okay. And so, plugging this into my calculator, this is what it is simplified to over here. So 75% of this many grams is shown here over the molar mass, which is 170. Okay, so to work out the moles of this value here, it is figured out and calculated over here. So that's going to come in handy very soon. So whenever you get a question where it's like, how much energy is produced for a certain amount, you are going to use this table method, this bit of ratios. So you're going to get information from the equation, which is over here, and you're going to compare it with the information that they give you from the question, okay? And what you're doing is the information you're looking for is moles against the energy produced. So in this instance, in the equation, we've got how many moles of kerosene used in the equation. This is kerosene over here. How many moles is used? How do you know? Look at the big number in front of this. It's 2. So 2 moles is used in the equation. For every 2 moles, how much of energy is used or given off? What's the energy associated with 2 moles? Look at the delta RH. So for 2 moles, you're getting 15800 kilojoules per mole, okay? 15,800 kilojoules per moles of energy is being released. So I'm popping that here. All right. Don't worry too much about the negative sign, okay? And so what we have is this ratio from the equation. We need to find the ratio from the question. So in the question, how many moles of kerosene is specifically used? Well, we've just calculated that here, so we could plug that into this. Okay. Right. Now, how much energy does this produce? Well, we don't know. That's what we're trying to figure out. So if 2 moles produces this much of energy, how much does this many moles of energy produce? Simple ratios. So how do we get from 2 to this value over here? What is the common multiplier? What do we have to multiply 2 by to get to this? Well, to figure that out, simply divide 11294 by 2 and you get the common multiplier. Try that yourselves. Pause the video. You should get this value over here, okay? So 2 times 5647 should get you to 11294. And please double check this in your calculator. Times 2 by this value here and see if it gets you to here. If not, you might have to, you might have done something wrong. You might have done 2 divided by this. But no, it's going to be this divided by this, and they'll give you the common multiplier and get you down to here. So if you do it to this side, if you times it by this value on this side, you have to do it on the other side. So this energy value, 15800 times 5647. So this energy value times by 5647 is going to get you the answer for how much energy this many moles releases. So by plugging that into my calculator, I got this value here. But remember, it's usually the 3 significant figures, and so I have got 3 significant figures, turn the rest to 0, and it's kilojoules as the unit because the moles per litre cancel out. Okay? Right. Next question. Kerosene is a non-polar substance. Use your knowledge of structure and bonding to identify and explain the solubility of kerosene in both water and cyclohexane solvents. Okay, so kerosene is non-polar. We've got to explain the structure and bonding and explain the solubility of kerosene in water and cyclohexane solvents. So what do we know so far? Well, you should know that water is a polar solvent. Cyclohexane, okay, it is an organic molecule. It is non-polar. What is the solubility of kerosene in cyclohexane and water? Well, remember, like dissolves in like. So in water, kerosene will it be soluble or not? No, because they're not like. Water is polar, and kerosene is non-polar, so it won't be soluble. But in cyclohexane, will it be soluble? Yep, because both of them are non-polar substances. So we're going to have to explain that and why. We cannot just simply state this, we have to explain why. Kerosene is insoluble in water and soluble in cyclohexane, which is what we've discussed over here. Next, I want to delve into this further and talk about the solubility in water. So remember, solubility can be explained like this. So water is a polar solvent. Addressing that is worth and achieved, as it contains a negative dipole oxygen and positive dipoles hydrogen. On the other hand, kerosene is non-polar. This means that the attractive forces between water and kerosene are weak and hence not able to overcome the forces of attraction or bonding within kerosene. That's a little bit tricky to visualize without any diagrams right now. So let me quickly sort of visualize that for you. So we've got kerosene over here. I'm just going to pretend that this is kerosene. I know this is not accurate at all. Okay, and then this right over here is water. So within kerosene, we've got bonding. Okay, we've got bonding over here. And so because water is polar and kerosene is non-polar, the attractive forces between kerosene and water are not strong enough. So there's not a strong attraction to pull kerosene apart. So the forces of attraction between water and kerosene are not strong enough to overcome the forces within kerosene holding it together, because water is polar and kerosene is non-polar. Okay? I hope that makes sense. So that's what I've discussed here. So now I have to talk about the solubility in cyclohexane. And so cyclohexane is a non-polar solvent like kerosene. As a result, the forces of attraction between cyclohexane and kerosene are strong enough to overcome the forces of attraction within kerosene. Okay, so let me do another little subpar diagram for you again. So we've got kerosene over here, and then we've got cyclohexane over here. Both of them are non-polar. So the forces of attraction between the cyclohexane and kerosene are going to be strong enough to overcome the forces of attraction within kerosene and break it apart. Okay, so it is going to be soluble because they are both non-polar. Like dissolves in like. All right, so linking back to the question. Therefore, kerosene is insoluble in water, a bit of a typo there, because it's a polar solvent, and soluble in cyclohexane, which is a non-polar solvent. Oh, what am I doing here? Okay, and so blue concepts are merit, pink concepts are achieved points, and discussing both of these, okay, all these points is worth an excellence. Question 3, we're almost there. Draw the Lewis diagram for the following molecules and name their shapes. Classic question, good to know how to do these every time. Okay, so this is what I love to do. So we've got AS, we've got 3 Fs, valence electrons. Let me get out the resource sheet for this. AS is positioned in group 15, and so what's the second digit of 15? It's 5, so that tells us there are 5 valence electrons. Fluorine is in group 17, second digit of 17 is 7, so that means fluorine has 7 valence electrons. The next column is going to be how many more electrons does the atom need for a full outer shell. So according to the octet rule, atoms need 8 electrons in their outside shell to be fully stable. However, there are a few exceptions to this rule, which I would love for you to know, okay? So these guys over here don't follow the octet rule. They're like the naughty kids in class. They don't follow the rules. And instead of needing 8 to have a full outer shell, hydrogen only needs 2, boron only needs 6, and beryllium needs 4. The way I like to remember this is using a silly little sentence, and it goes something like this. You have to be 6 times better than B4, okay? It's a little bit roundabout, see if you could come up for something for yourself, but that's how I remember it. You have to be 6 times better than B4, okay? So, back to our little Lewis diagram. So, AS needs 3 more to have a full outer shell. It currently has 5, so it needs 3 to have a full octet. Fluorine has 7, so it needs 1 more to have a full octet. And so our needs column also tells us how many bonds each atom will form. What we have to do next is we have to identify the neediest atom. So the neediest atom out of all of this is AS, because the reason why is because it needs 3 electrons. Okay, every other atom, fluorine, needs only 1 to have a full outer shell. So AS goes in the middle. The rest goes around the outside. So according to the needs column, yes, AS needs 3 bonds, 3 electrons, which means 3 bonds. So I'm going to draw that around AS right now. Fluorine only needs 1 electron, aka 1 bond, and that's shown in the diagram. So the next thing we have to do is we have to make sure that every atom has a full outer shell of 8. So currently we have AS, it has 1, 2, 3, 4, 5, 6. Remember, 1 bond counts for 2 electrons. Because it only has 6 right now, we have to add 2 more electrons to make it a full outer shell. So now it's got 8 around it. Fluorine, let's count how many it has. So this fluorine atom, each fluorine atom has 1, 2 electrons around its outer shell. So to make it happy, we need to add a few more electron pairs. So it's currently got 1, 2, 3, 4, 5, 6, 7, 8. Let's do the same for the other ones. 1, 2, 3, 4, flash you the answer. 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so we have to name the shape for this, and the shape for this is, well, let's have a think about it. We've got 3 bonding regions and 1 non-bonding region. So this must make it what? Trigonal pyramid. Think of it as having, think of it as a little bit of a tripod, so it's got 3 legs, and then the top lone pair is like the camera on the stand. So it's the tripod forms a little bit of a pyramid shape with the 3 stands and the camera on the top. Okay. So the next atom we have to look at is H2S. The next atom we have to look at is H2S. So again, let's draw a table. So I've got 2 H's and an S. So valence electrons. How many does H have, hydrogen have? So hydrogen is in group 1, so it has 1 valence electron. So we've got sulfur. Sulfur is in group 16. Second digit of 16 is 6, so it has 6 valence electrons. How many more do each of these atoms need to have a full outer shell? Hydrogen is our exception over here. It needs 2, currently has 1, so it needs 1 more to have a full outer shell. And sulfur, it is not on our list of exceptions. It follows the octet rule. It currently has 6. That means it needs 2 more to have a full outer shell. Which one is the neediest atom? Which one has the most needs? Yep, it is sulfur, so it is going to go in the middle of our diagram. Everything else will go around it. So sulfur, according to our needs column, says that it needs 2 electrons. Sulfur needs 2 electrons, so that means it's going to form 2 bonds. So let's draw these 2 bonds. Hydrogen, according to our needs column, needs 1 electron. So it is going to form 1 bond. So let's check if everything is happy. Does sulfur have 8 electrons around itself? It's got 1, 2, 3, 4. So we have to add a few more. 1, 2, 3, 4, 5, 6, 7, 8. Hydrogen, does it have 2 electrons around itself? It's got 1, 2. Yep, everyone's happy. Alrighty. Okay, last molecule, let's draw a table. So I've got 2 fluorines, a carbon, and an oxygen. Okay. Valence electrons. Number of valence electrons for fluorine is 7 because it's in group 17. Valence electrons for carbon is 4 because it's in group 14. And 6 valence electrons for oxygen because it's in group 16. How many more electrons do each of these atoms need for a full outer shell? Fluorine needs 1 more to have a full outer shell of 8. Carbon needs 4 more to have a full outer shell of 8. And oxygen needs 2 more. Which one is the neediest atom? It is carbon because it needs 4 electrons. Let's place everything else around it. Okay, carbon needs to form 4 bonds. However, there are only 3 atoms around it, so how can it form 4 bonds when there's only 3 things around it to bond with? That means it's going to have to form a double bond with one of these atoms. Which atom is it going to be? Well, as you can see, fluorine only needs 1 bond each because it needs 1 electron each. But oxygen needs 2 electrons, therefore 2 bonds. So it makes sense that the double bond, will occur between carbon and oxygen. So the rest of the bonds will occur with fluorine. So now there's 4 bonds around carbon, which satisfies that. And fluorine has 1 bond each, which is cool, and oxygen also has 2 bonds. So everyone's happy, but we need to check if everyone's truly happy, because we need to make sure if each of these atoms have 8 valence electrons around itself. Carbon has 1, 2, 3, 4, 5, 6, 7, 8, so that's happy. Fluorine has 1, 2, so we need to add more. 1, 2, 3, 4, 5, 6, 7, 8. Do the same for the other fluorine. 1, 2, 3, 4, 5, 6, 7, 8. And oxygen has 1, 2, 3, 4, 5, 6, 7, 8. Now it's happy. All right. What I didn't go over is the shape for the previous molecule. So let's do that. The shape for H2S, well, it's got 2 bonding pairs and 2 non-bonding pairs. So it's going to be bent. Okay. The shape for F2CO is trigonal planar because there are 3 bonding pairs and 0 lone pairs. Alright. So what I like to do is I would first like to talk about the regions of negative charge, Vesper theory, geometry and shape. Okay, so let's see what I've written. Now, N2O has 2 regions of negative charge around the central atom end. This is one region, this is the other region. These regions repel for maximum separation into a linear geometry. So I've linked Vesper theory with geometry. Remember, like charges repel, and because there are these 2 regions, they repel for maximum separation. And that separation results in a geometry, which is this. This results in a bond angle of 180. Now we're talking about shape. Since there are 2 bonding regions and no non-bonding regions, the shape is also linear like the geometry. So geometry and shape are different things. Geometry is based on the number of negative regions, and shape is dependent on the number of bonded and non-bonded regions. Okay, so in contrast, N2H4 has 4 regions of negative charge, as you can see here, 1, 2, 3, 4. These regions repel for maximum separation into a tetrahedral geometry with a bond angle of 109.5. So I'm comparing the bond angles. Since there are 3 bonding regions and 1 non-bonding region, N2H4 has a trigonal pyramidal shape. And they are worth excellence points if you refer to both and draw the links for the same things for both molecules, and that's overall an excellence. So, what we have here is another fuel that could be used in rocket engines, methane, and it reacts with oxygen. Use the change in enthalpy for combustion of methane and the bond energies listed below in the table to calculate the average bond enthalpy of the CH bond in methane. So we've got methane over here, but we don't know the energy values in each of these CH bonds, and that's what we have to figure out. So the way to work out bond enthalpy questions is using this equation here. And so it's the bond enthalpy equals the bonds broken, which is this side of the reaction, the left side things of the reaction, minus the bonds formed, which is everything after the arrow on the right hand side. So these are the bonds formed, minus one from the other, and we could get our bond enthalpy. However, we know our bond enthalpy. We're going to just have to rearrange things to find the bonds broken, especially this one. So I've created a little bit of a structured response here, calculating everything nice and clearly. And so bonds broken, let's calculate all the bonds broken, which is everything on this side. They've drawn diagrams for us here. So CH4, it's got 1, 2, 3, 4 CH bonds. So it's 4 times CH bond, but because we don't know what the CH bond energy value is, I've written that as X. Now we've also got 2 O2 molecules. So what I like to do is I actually like to draw it out. I've got 2 O2 molecules here, and so that means I'll have to times this value by 2. Okay, so I've got 2 times the OO bond, and that's 2 times 495, and I get 990 kilojoules per mole. So those are the bonds broken. The expression for that, you'll see that very soon, but let's calculate the bonds formed, which is everything on this side. Okay, and they've drawn those over here. Okay, CO2. CO2 has 2 CO bonds over here, so we'll have to times that by 2. So 2 times CO is the same as 2 times 805, which is 1610. And we've got 2 H2O molecules. So let me draw that here. Oh, let me draw that a little bit better. As you can see, we've got 1, 2, 3, 4 OH bonds. So we're going to have to times the OH value by 4. So I've done that here, 4 times 463, and that's 1852. So now we have to plug everything into this equation here. Okay, so we've got the delta RH as given by the question, and then we've got the bonds broken over here. So it's 4x plus 990, and I've written that here. Okay, and if you write the expression, that's worth and achieved. Okay, so bonds broken minus bonds formed. So I've got 1610 plus 1852 written over there. Okay, the next thing that we have to write is we have to make sure that we are simplifying the like terms. And so 1610 plus 1852 is 3462, so I've simplified that, and I could simplify it even further. So I've got 990 minus 3462, and that equals negative 2472. So 4x minus 2472, let's simplify that further. So I can isolate 4x, make it go all by itself by cancelling out the negative 2472. The way I do that is plus 2472. If I do it on this side, I have to do it on the other side. And that results in 4x equals 1670. To get x on its own, I can divide this side by 4 and cancel this out. And that means I have to divide this side by 4, and that results in x equals 417.5. Three significant figures will give us 418, and that's kilojoules per mole, and that's how much this bond is worth, and that gives us an excellence. Alright, next question. Calculate the mass of methane required to react in order to release this much of energy. Okay, so this is going to be pretty easy to calculate. You just have to figure out some simple steps. So, what to do in this instance? We've been given some information here. Okay, we've got this, and we want to figure out the mass. And then we've got energy, we've got molar mass, and we're dealing with CH4. Okay, so what to do? Well, let's first work out the moles of CH4. Okay, we want to work out the moles of CH4. One way of working out moles when you don't have the mass is by using this equation here. So U over E. U stands for energy wanted, and the energy wanted is this. This is what you want some mystery mass to release, okay? So that's up top. EH is going to be the energy that you already have in the equation, so that's this right over here. So, to work out the moles of CH4, you go 1660 over 802, and you get 2.07 moles. Alright, the next step is to then plug in this value here. We've got given the molar mass already, so we could plug that in here and rearrange to find M. So, I've got 2.07 equals mass over 16, which is the molar mass of CH4. Rearrange that, so I divide both sides by 16. This cancels it out on this side, so I'm just left with M times, and then on this side I'm timesing it by 16, so I get a mass of 33.1 grams, and that's worth a merit. And achieved if you get one step correct. Okie dokie. So the Lewis diagrams of phosphorus chloride, trichloride, I like to call it pickle 3, and boron trichloride are shown below. Both molecules contain 3 chlorine atoms around the central atom, but they have different polarities. Circle the word that best describes the polarity of each molecule. So let's have a look at phosphorus trichloride. As you can see, an instant giveaway that it's polar is the fact that it has lone pairs of electrons, okay? So this is going to be polar. Okay, for boron trichloride, same atoms, but there are no lone pairs, so you can be confident that it is going to be non-polar. Compare and that's worth an achieved. Compare and contrast the factors that influence polarity of these two molecules. PBE, that's what I'm going to talk about first. PBE stands for polar bonds and electronegativity. So let's count the polar bonds around PCl3. I'm going to start off with that one. So PCl3 has 3 polar PCl bonds, and I've drawn the dipoles, with Cl being the most electronegative. This means Cl has greater attraction on electrons, which makes Cl slightly more negative and gives it this dipole. The next thing I want to talk about is symmetry. S for symmetry. And within symmetry, I have to talk about shape, I have to talk about the atoms, and I have to talk about the lone pair of electrons, whether they're there or not. So, PCl3 has a trigonal pyramid shape and the same atoms around the central atom P. However, due to the presence of a lone pair of electrons, the polar bonds are not arranged symmetrically around phosphorus. Okay, then I talk about the dipoles and whether they cancel out or not. As a result, the bond dipoles do not cancel out because it's not symmetrical, okay, which accounts for a molecular dipole. So overall there's a molecular dipole where one end is more negative than the other ends, okay. So, tying it all together, therefore PCl3 is a polar molecule, okay. In contrast, I'm going to follow the same structure to answer for BCl3. Okay, so BCl3 has 3 polar BCl bonds, with Cl being the most electronegative. Again, this means Cl has a greater attraction with electrons, making Cl slightly more negative than B. BCl3 has a trigonal planar shape, I'm talking about symmetry now, has the same atoms bonded around boron, and no lone pairs of electrons. This means the polar bonds are arranged symmetrically around boron. As a result, now I'm talking about the dipoles, as a result the bond dipoles cancel out, which accounts for no molecular dipole, okay? There's not one end that is more negative or positive than the other. Therefore BCl3 is a non-polar molecule. And that is worth an excellence, and that's the end of the exam. All the best, hope you had fun. I sure did.